So yeah, welcome everyone. My name is Kilian, and this is the second time that I'm speaking here at emBO++ now, and I'm very glad to be here. I must say that it wasn't obvious that I would be here this year as speaker, because I have to confess that I'm not an embedded developer. So I'm mainly working on desktop applications and libraries. Yeah, but so when the call for speakers started a few weeks ago, then I first didn't submit any talk, and was just watching the speakers page, filling with other great speakers and talks on the emBO.io website. But then there was a talk submitted from Paul that he gave as the opening talk today. And when I read through the abstract, it actually said something about that ranges might be a game changer for the embedded world. I think he quoted Odin on that one. And that was the moment when I thought, like, yeah, the embedded world is also into ranges, exactly like me, and thought, yeah, that's the sign. I'm going to submit a talk, and that's why I'm here now today. I'm talking about deduction guides for range adapters. Please feel free to ask questions, and I will answer all of them at the end of the talk. All right, so C++ added ranges. So the currently latest standard of C++ added this great, huge new library feature. And I've listed the different compilers and standard libraries and the versions since when this is available. And yeah, this is the first version since the feature is available for those. And after the first releases in these different libraries and compilers, there have again been several defect reports that got added to C++ 20 retrospectively. And also C++ 23 will add further features to the ranges library. So what I want to say is that the C++ standard and the documentation that you can find on CPP reference and all the STL implementations are very likely not synchronized. So it's difficult to find something that is working in every library already. And they're basically not always in sync. And if you think that you'll just go and figure it out, it can work, but I must say that the compiler errors are also very hard when working with the ranges library and making mistakes. I tested it recently, and GCC was pretty good now, but Clang and MSVC still have some issues. And yeah, probably it all boils down to how good your compiler is in generating error messages for concept violations. But luckily there are a lot of good talks which I can recommend. I watched the talks from Tristan at the last 3 CPP conferences. He presented at each year a talk about ranges, which I can very much recommend, and also the talk from Jeff is very good, and probably there are also a lot more good talks about ranges. And I can recommend you these talks if you want to learn how to work with ranges. But there's still a reason that I created this talk that I'm giving you today, because there was one thing in all these talks that I simply didn't understand. It was briefly mentioned from time to time, but yeah, it was never explained in depth, and that's what I'm going to explain now. So the ranges library is very broad. We have additions to the iterators library. Some things which I want to highlight is that, for example, a range no longer gets denoted by a begin iterator and an end iterator, but for example by a begin iterator and a sentinel now, which can be a completely different type as long as it satisfies certain requirements. On the other side, we have a lot of changes in the algorithms library, which would be interesting. For example, the algorithms like std ranges find, std ranges find if, and so on, are no longer don't take two iterators anymore, but they are now overloaded on an iterator and a sentinel, which is, well, of a different type, and also on a range. And yeah, there are also a lot of other changes, for example, that the algorithm take projections now, which you can apply to an element before the algorithm does something with it. And while in C++ 17, all the algorithms call the operator callable, or just call all the predicates and all the actions that you plug in, for example, in find if. This changed now for the ranges algorithm to work on std invoke, which is slightly more powerful. But that's just a side note. I think that's very interesting and good to know, but what we will be talking about are the range adapters. So this talk is about range adapters. We have several of them: filter view, transform view, take view, and so on. And we'll explore those a little bit. There's a standard example that you see in most of the talks explaining range adapters, and it goes the following way. You declare some kind of container. In this case, it's std array. And in case that this syntax looks unfamiliar to you, this is the C++ 17 class template argument deduction, which is very similar to function template argument deduction, but well, it works on a class now. So the type of A will be std array of int, 4. Pretty straightforward, I'd say. Then we have a predicate called isEven, which returns true if a given integer is even. And now we can pipe our container A into a range adapter object, std views filter, which takes a predicate and will return us a filter view, which we store in even values. And then we can iterate over even values and, obviously print all the even values because std views filter is a filter in, so everything that satisfies the predicate will be in that view. And 4 and 2 are the even numbers, and 5 and 7 are odd and therefore excluded. We all think of C++ as a very efficient programming language, and we naturally expect that this is efficient as it can get, and therefore we don't expect that the container A would get copied, right? So piping A into std views filter is constructing a lazy range adapter object, and then earliest when we iterate over it, it will check, okay, what values are in R? Do I have to skip them? Do I have to return them? And it will just have a reference to A and not copy the whole array. And the typical talks about ranges then go on and show you a second example where you again have your array A, you have your predicate isEven, by that you filter, and now you have an action square which takes an integer and returns the square of it. And then the example shows how you can chain these range adapter objects. So we pipe A into filter and that result into transform. And the result of that will be 16 and 4. So we first filter the even numbers. We have 4 and 2 and transform them. So we have 16 and 4. And at that point, the talks typically just go to another example whatsoever. But this is the point where I have my contradiction. So if we pipe A into views filter, then this constructs a filter view which holds a reference to A. If we pipe A into std views filter and that afterwards into std views transform, then this constructs a transform view, but it has to hold a copy of the filter view, right? Because A piped into filter gives me some R value, and std view transform can't have a reference to that RValue. So it has to take it by value. But how does this distinction work? I mean, is this specific to range adapters? It turns out that it's not exclusively specific to range adapters. I can even go further and have an R-value array and pipe that one into std view's filter. And yeah, this time even values has to store the array by value, right? Because it's not a reference, not an lvalue I can never bind a reference to. Okay, so to explore this further, I want to give introduce a few concepts and classes. The first, and maybe I want to briefly introduce concepts. So concepts are, for the sake of this talk, are compile time predicates, like std is void v or std is const v or something like that. I will. You can use ranges, or you can use concepts also for this. So we can use the concept std ranges range, plug in a type, and then it returns true if it satisfies the concept and is a range, and false if not. And the concept range is satisfied by a type which gives you a begin iterator and an end sentinel. Typically by either calling the member function begin and end, or by calling freestanding functions begin and end. There's some kind of logic in the ranges library how to actually call begin and end. That shouldn't bother us now. And we have the concept view, which is a refinement of range. So to satisfy view, you have to be a range and do more. And you at least need to be movable. And you don't necessarily need to be copyable, but if you're copyable, then this should also be cheap. Like, you would be fine to take a view by value if you have a function. No one would complain in the code review if you take a view by const ref or by ref or by value. It's fine. So it's cheap to pass around by value. I'm actually slightly struggling to explain view because it's not that easy. So if you write a type, it's not like the concept view could detect if it is a view or not. You have to opt it in. So this now goes beyond the detail of this talk, but basically you have to specialize a variable template and set it to true to indicate that this type is a view now. And this also got, what a view is also got changed in October, I think. There was a defect report that got voted in with the title, What is a View? So the standard also just got that clear a few months ago. String view is obviously a view. The range adapter objects like filter view are obviously also views. And I put the directory iterator here because I find that quite interesting. We have two iterator types in the STL, directory iterator and recursive directory iterator, which are both an iterator and a range and, well, also a view. Just as a side note. Okay, then we have two classes, which I want to briefly mention. Std ranges ref view and std ranges owning view. These are both ranges, and these are even views, and they provide the classic view interface like begin, end, size, empty, and so on. And what they do is they just wrap another range. So the difference is that ref view stores the range by reference, and the owning view stores the range by value. And I've shown this in the example here. We have a string text, and when I construct a ref view, I'm again using class template argument deduction. When I'm constructing the ref view of std string actually, then this holds a reference to text. And when I construct the owning view, then this takes a range by rvalue reference and stores it by value within the object. Owning view is move only, it's not copyable, but that's just a side note. And well, if you iterate over a ref view or an owning view, it's like iterating over the underlying range. And yeah, I know it's an amazing feature that the ranges are going to change anything. No, this is just keep that in mind. We get to that later. So back to the contradiction that we want to resolve. So for further exploration, we have to rewrite the code now slightly. So on the left side, we pipe A into the filter. On the right side, we pipe A into filter and afterwards into transform. The next thing to know about range adapter objects is the 3 different ways we can invoke them. So that's just like some syntactic sugar. We've seen the way of piping it into an adapter. You can also call the adapter with some arguments like the isEven predicate, and then you again get a callable which you can then call with your container. Or the last way is to call the adapter first with the container and then with all the arguments. And syntactically that's all the same. So we use this rewrite of our range adapter objects to switch from the first syntax to the third one now. Okay, and got that one. The next topic is expression equivalence between the range adapter object and the range adapter type. The range adapter objects did use filter when called with 2 arguments is expression equivalent to a constructor call of the range adapter type std ranges filter view with these 2 arguments. And the same applies to transform and transform view. They're also expression equivalent. And at the end of the talk, we'll see which range adapter objects are actually not expression equivalent to their range adapter type. Yeah, and expression equivalence, means that it's the same. It's like completely interchangeable what you write there. Yeah, and we use this code transformation now to rewrite the code. But you might guess it already. Filter view and transform view are no classes. They are class templates. And I can't construct a class template. I have to instantiate it, then I get a class, and then I can construct that one, right? So we will have a short detour into class template argument deduction now. That feature gets abbreviated with CTAD or CTAD. It's available since C++17, and it's a very similar approach as with function templates, which we use, I don't know, since C++98, I'm not sure, but it's very common, right? We call stdmin of 1 and 2, and there is no function stdmin taking 2 integers, but there's a function template. The compiler will instantiate it for us, and we can call that. Some examples. If you construct an std pair with 2 and 4.5, the compiler will deduce that it's a std pair of int double. I think this is quite handy with logguards, for example. And it's also very handy, I think, with std experimental scope exit. This is a completely macro-free implementation, library-based implementation of scope guards. Which benefits heavily from class template argument deduction. The compiler is most of the time able to do the deduction himself, but we can actually also provide him deduction guides to guide him through the way of deducing the final class from the provided arguments. So this is our first deduction guide now. We have a class template called text, which is templated on one type, and the deduction type that we provide is this syntax of like writing a constructor declaration, then the arrow, and then what you want to deduce. And the meaning is that if somebody is going to construct a text with a const char pointer now, then the compiler will deduce text of std string view. And in our sample now, we're constructing it, actually with a const char array reference, right? And these string literals are not directly pointers, const char array reference of some static size, but it decays to a pointer. And then the compiler will find this deduction guide. It happens with similar rules like overload resolution, I think. It finds this deduction guide, and the type of sample will be text of std string. Now we have a second deduction guide, which is slightly more complex. We have a class template holder, and now we have an alias template called box, which is templated on one class X. And it evaluates to std conditional t. That's like a compile time predicate where you put a condition, a true type, and a false type. And yeah, it's like the ternary operator for types for metaprogramming. So if X is an lvalue reference, then box evaluates to std reference wrapper of X without its references. And if X is not a lvalue reference, then box will simply evaluate to X. Our deduction guide for holder is now a template itself. And we have a forwarding reference u that we take as argument, so u refref, and deduce holder of box of u. If we now construct the holder of A, we plug in an R value of type double. And if we construct a holder B, then we plug in an L value reference of std string. And yeah, what will this deduce to? The first example, A, will deduce to holder of double, because it will instantiate the deduction guide with u equals double. So when u is double, then box of double is, well, double. And for our sample B, it will deduce holder of reference wrapper of string, because it instantiates the deduction guide with u equals string ref. Yeah, I hope that the forwarding reference are clear so far. Otherwise, please ask questions and I will go on that after the talk. But now we have that one, and now we go to our last deduction guide. Coming very close to solving the mystery now. We have a type called myRangeAdaptor, and we have now an alias template called myAllT, which takes a class X. And this is now slightly more complex. It first checks if the type X is a view, then it just evaluates to the type X without its CVRef qualifiers. Otherwise, it checks is type X an L-value reference, then it evaluates to ref view of X without its ref qualifiers. And as the third fallback option, it evaluates to owning view of X without its ref qualifiers. We now have a deduction guide again, a user provided one, taking some class R and a universal reference to it, or forwarding reference, and deducing to myRangeAdaptor of myAllT from R. So we have a few samples now. myRangeAdaptor A, which gets initialized from std string view. We have an std array R, ARR, and we are going to initialize the range adapter B from the reference ARR. And we have the third example, myRangeAdapter C, where we plug in a range, an R value reference to a range, which is not a view, std string. And yeah, these three samples match exactly the three cases of the myAllT. So in the first case where we have a view, it deduces to myRangeAdaptor of view. In the second example where we have a range which is an L-value reference, it deduces to myRangeAdaptor of ref view. And in the third example, to myRangeAdaptor of owning view. And this is kind of the mystery that we that hides behind the range adapters, because, well, deduction guides or range adapter types also have deduction guides, which take the R by forwarding reference or the range by forwarding reference and deduce filter view of std views all t of R. And std views all t is very similar to the my all t that I just presented on the slide before. Not completely, but yeah, very similar. So putting it all together, I just removed the line breaks that it fits all on the slide here. Taking the code from the beginning and introducing a few alias templates such that we can give the lambda expression some names. So we have our array A, we have the predicate is even, we have the function square, or the functor. We have the even values, where we pipe only A into std filter. We give the even values a name, or the type of even values a name, filter view type. We pipe A into filter and then into transform and store that into square of even values. And what then happens is all the steps that we just went through. So first, we can imagine that we would rewrite the adapters. This is expression equivalent to the constructor call of the corresponding range adapter type, filter view and transform view. Then class template argument deduction and our deduction guides kick in. And this is where you see the difference already, right? So we have filter view of std views all t from A ref. And in the other case, you have transform view of std views all t of the filter view type. And yeah, finally, std views all t reduces to ref view of the array in the uppercase, and in the lowercase, it's just the view type. And yeah, that is the magic. So to summarize this, most range adapter objects are expression equivalent to the range adapter type. And the range adapter type has a deduction guide which uses forwarding references and std views all t to get the final view type that it's going to store. And std views all takes a viewable range and turns that into a view, and it does that by checking, is it already a view, like string view, then it returns just that one. Is it an L value, then it returns a ref view over that L value, and if it's an R value, well, then it will be an owning view. And this explains the different behavior between these two otherwise very similar looking cases. Two short bonus slides that I would like to share with you, because I talked a lot about std views XXX and std ranges XXX view. What is actually the difference between those two? I think this slide is, yeah, maybe it has too much content to go all through it by now. So I can recommend you to go through the range adapters on CPB reference maybe. But in general, most of these are expression equivalent. But a few of them do more. For example, views take. If you have a string view, A, B, C, D, E, and you say, yeah, I want to take the first 3 characters of that string view, then it wouldn't make much sense to construct a whole ranges take view that stores the inner string view, because, well, what is it? You take a new string view which has the same begin pointer and just a smaller size, and there you are. So these views classes contain more logic. They're slightly more intelligent, and this is also the recommendation that you get from experts in that field. If you ask them which of these two kinds you should prefer. So the guideline is to see these std ranges XXX view classes as implementation details, and to prefer using the std views XXX classes. And yeah, Eric Niebler seems to actually be sorry that they're not implementation details. And I'm more sorry that I've talked so much about those now and explained so much about them. Yeah, but I hope you enjoyed listening to this detour about ranges. Yeah, I'd say more kind of an implementation talk than a pure user overview, but nevertheless, I hope you enjoyed it, and I'm happy to go through the questions now if there are any. No, it's fine. Yeah, great. Thanks.